Hey there. We're going to go ahead and get started. My name is Tyler. I'm an instructor with Manhattan Prep, and this is a free GRE prep hour. And today we're going to be talking about something called function shapes. So if you've never been to one of these before, the way this works is I am hosting this session live in Zoom right now. It's going to be uploaded onto YouTube later. So whether you're in the room with me now or whether you're checking this out on the internet sometime in the future, big welcome to you. Good to have you here. And if you're in the Zoom room right now, why don't you open the chat box and tell me where you are connecting from? All right, we got some New Yorkers. I used to live in New York during the pandemic, actually. It was a wild time to be in the city for all that. Um, got some Texans. I used to live in San Antonio when I was a kid, so go Spurs. Wembenyama is taking over. Um, got some Californians as well. That is where I live currently. I'm in the San Francisco Bay Area. But yeah, as I mentioned, we're going to be just going deep on a math topic for the next hour. So without saying too much more, I just want to show you all a problem to get started. So if you're in the Zoom room, take a look at this one and chat me your answer when you think you've got it. If you're watching on YouTube, feel free to pause the video. Here is your first question. So one way to approach something like this would be to pick some values for x and take a number picking approach, which there's nothing necessarily wrong with that way, but I want to show you a technique that I find is usually a little bit faster. And it's something that revolves around knowing the shapes of different functions and kind of visualizing what these things look like. The most basic shape is a linear shape, right? If y is just equal to x, that's just a straight line. And then for a more advanced function, if you have x squared or any even ordered power on x, you're going to get this curved U-shaped parabolic function. And then if I had any odd powers like x cubed, x to the fifth, etc., you're going to get this kind of like curved where basically this half of the parabola has been flipped upside down. So if I'm really familiar with those shapes, that's going to allow me to tackle something like this with a good amount of speed. Because I know it must be true that x cubed is less than x. So in my head, I'm going to think, okay, x itself, that's just a straight line. And then x cubed, I'm going to draw that in. It's going to start off higher than x itself until I cross over 1. At 1, it's going to dip down for fractional values, for positive fraction values of x. Then it's going to curve around until I hit -1 and then come out like that. So I'm just overlaying the linear and cubic shapes. Now, where is x cubed smaller than x? In other words, if I just took like a single vertical slice of this graph, where is my green line underneath the red line? Well, it's going to happen in a couple spots. The green line is below the red line right here and right here. In other words, having this visual allows me to determine that the domain of x, that is the values that x could possibly be, it's either going to be positive fractions or negatives that are more negative than -1. So now that I'm clear on what x could potentially be, I can look at my two quantities. And compare, okay, what would x as a positive fraction be? If I just pick like 1/2, then 1/2 squared would be 1/4. So that's a case where quantity A is bigger. Or I need to test something that's in the negatives down here. So if x were -2, x squared would be +4. And that's a case where quantity B is bigger. So I've gotten two different relationships. Sometimes A is bigger, sometimes B is bigger. That means we've proven that the answer is D. So let me show you a similar problem. And I want you to see if you can take this kind of function visualization approach to figure out what the potential values for the variable would be. Try this one. So the first thing I'm going to do here is do what I can to simplify this upfront information. That n to the fifth minus n cubed is less than 0. I'm going to get that into a form that's a little more digestible. So first thing I'm going to do is I'm going to add n cubed to each side. So I think that makes it a little easier to see versus comparing to 0. I'm just comparing my two n functions now. So this tells me the fifth needs to be smaller than the cube. But I can actually take it a step further. Because these are both bases of n, I can divide out an n squared from each side. Now, why am I dividing n squared rather than just a single n? Good. I see some people getting this in the chat. N could be negative, and if I were to divide by a negative, that's going to flip that inequality symbol around, and I don't want to do that. But n squared, squares are guaranteed to be positive here. So if I divide that square out, then I get this form, that n cubed is smaller than n. And now you might be getting deja vu because this is pretty much the exact same information we had in the previous problem. So again, I'm going to grid this out. So a straight line, that would be n to the first, just a linear line like that. And then my n cubed is going to be this kind of zigzag curvy shape, looking something like that. So once again, where's the cube smaller than the first? The cube is smaller there and there. That means my domain is either positive fractions or negatives that are smaller than -1. And I'm going to do a similar move to simplify my two quantities, kind of like what I did to the upfront info. I don't like having this kind of longer expression in quantity A. I'm just going to add an n to each side, so that what I'm actually comparing is just n squared versus n itself. And it's the same thing as the last problem. If I had a fraction, if n were 1/2, n squared would be 1/4. So that's a case where quantity B is bigger. But if I had a negative value like -2, n squared would be +4. That's a case where quantity A is bigger. So I have two different relationships, and I've proven my answer is D. So I like to use this technique. It's often on quantitative comparisons where there's just one variable involved, and I'm looking at functions of that variable, like often squares, cubes, fourth powers. And we're going to go a little heavier on this domain finding here. So if you've got some questions in the chat, I see a few people asked about this. I want to take a look at some other scenarios. So this first one, this is similar to what we've already been looking at. If I'm comparing two different odd powers, like a first power versus a cube power, the first power is just a straight line. And then I'm going to draw in my hashes for 1 and -1. And the cube crosses over at 1 and then goes under, and then crosses 0 and goes over, and then crosses -1 and it's back under. So the areas where the first power is underneath the cube, right, where the red line is under the green line, that's my positives bigger than 1, and it's also my negative fractions. And for the opposite, if I wanted my first power to be larger than the cube, that happens in two spots. First power, the red line is on top for my positive fractions, and the red line is on bottom when I have negatives smaller than -1. So let's keep going. I want you all to try and chat me answers for this next one. If I want a square to be smaller than the fourth power, what's my domain of x? Where is that possible? So a square is going to have this kind of parabolic shape, something like that. So if I call that the square, how is the fourth power going to look in comparison to a square? Well, you know it's going to be equal at 3 points. The square and the fourth are equal when my input is 1. Then they're going to both output 1. When my input is 0, they're both going to output 0. And when my input is -1, they're both going to output +1, right? -1 squared, -1 to the fourth, those are both +1. But what's different is because I have a higher power here, for my large positives, my positives that are bigger than 1, it's going to be a bit steeper. So my blue line is going to be on top of the purple line until I hit 1. And then for my fractional positives, the fourth is going to be less, because when you multiply fractions, they get closer to 0. Same thing for my negative fractions. The fourth is going to stay under that square until I hit -1, and then the fourth power ramps up again. So where is the square smaller than the fourth? It's those two areas on the outside. And if I want to look at the opposite, if I want my square bigger than the fourth, that happens anytime my input is a fraction. Okay, so we've seen what happens when I'm comparing two different odd powers and then two different even powers. Now I want to look at the case where I'm mixing an even and an odd. So the first variant here would be I have a square versus a cube. In other words, my odd power is the larger magnitude of the two. So I'll do my square in purple. Something like that. And then my cube, because it has more magnitude, it's going to be faster for those big positives. Then it connects at 1 and drops under. And then compared to a square, right? Even ordered powers always stay positive. When I have a cube, these ones are going to output negatives when the input is negative. So it'll look something like that. So where is the purple line underneath the green line? It only happens when I have positives bigger than 1. And the inverse, Where is my square bigger than the cube? Where is the purple line on top of the green line? It's for those other three zones. Basically anything smaller than +1. With the exception that they're going to be equal at 0. And in fact, that's kind of a similar thing up here, that you're going to get equality at -1 and zeros for a lot of these. So in my head, I'm kind of always thinking about 7 areas. There's 3 numbers, -1, 0, and 1. And then there's 4 ranges. I've got my large negatives, my fractional negatives, my fractional positives, and my large positives. So when I'm number testing, or I'm just trying to figure out like where these functions might overlap, those are the big 7 that I'm trying to visualize when determining the domain. Okay, we got one last scenario here. It's when we have a mix of powers, but this time I'm making my even ordered power a larger magnitude. So for this case, we can imagine, what if I have a linear, just x to the first? I'll draw that in red. And then my square, put that one in purple. So square is going to be on top until it hits 1, drops down below, but my square stays positive over there. In fact, I do that a little bit sloppy. I can do that a little better. Something like that. Looks a little cleaner. So where is the first power? The red line under the purple line? It's in 3 different spots. It's for my big positives, for my negative fractions, and my big negatives. The opposite's going to be true only for positive fractions. Now, what I've got up here, this isn't necessarily something to memorize, but ideally, I want you to be able to be familiar enough with these shapes so that if you saw any one of these pieces of information as the upfront information in a quantitative comparison, you can kind of visualize what those shapes would look like and then determine the domain of X from there. So let me give you all another problem to try. Take a look at this one. So first thing I'd like to do here is take my upfront info and add x squared to each side. So now I'm just comparing my two functions. And I want the fourth power to be smaller than the square. And that's actually the same diagram we just drew, where that purple line is the square and that blue line is the fourth power. So where's that purple line on top? It's inside that range. It's only when my input is a negative or a positive fraction. So knowing that, whether you want to do this mentally or actually pick some numbers, right? I could either have a positive fraction like 1/2 or a negative fraction like negative 1/2. No matter what, the absolute value of that is going to be smaller than quantity b. So b is always going to be greater. And I had someone in the chat mention this, that if you wanted to, you could try and keep simplifying that upfront information. And at that point, you'd get x squared is less than 1. With one caveat that you're, assuming that x is not equal to 0, because you don't want to divide by 0. But it's the same thing. Where is the output of x squared smaller than 1? It's only when that input is a fraction. So even if you do it that way, you should still get b as the answer. Okay, so at this point, I'd say we're pretty familiar with the basic shapes, linears, parabolic, and cubic functions. And now I want to show you some ways that the GRE might start to modify some of those functions. And the first of those is going to be absolute value. And what introducing absolute value to the entire function will do is make it so that function cannot drop below the x-axis. So on the left, I just have y equals x. On the right, if I wrap that x in absolute values, it can no longer go negative right here. It's got to flip up to stay positive. Or similarly, if I wrapped a cubic in absolute value, right, this chunk that was going negative before, now it's flipping up. So everything is staying positive in quadrant 1 and 2. So doing this to a cubic effectively makes it look like a parabolic function, right? It's that U shape that we typically see with even ordered powers. Another common modifier is if you introduce a negative to the entire function. And what that is going to do is flip everything vertically across the x-axis. And I want to make sure you're conceptualizing this. It's a vertical flip. I know you could conceive of it as being a horizontal flip across the y-axis, but that's just kind of an illusion, right? You'll have a much easier time with this if you think of it as a vertical flip. So there it is linearly, or if I did it to a cubic, same thing. We're flipping it vertically across the x-axis. So that moves up, and that moves down. So using that new information, I've got another quantitative comparison for y'all to try. Let's give it a shot. So in my upfront info here, the absolute value of x cubed is less than 64. So normally x cubed is that kind of cubic shape, but the fact that it's wrapped in absolute values is going to turn it into that more parabolic U shape. So I get something that looks like this. And then the fact that it needs to be smaller than 64 means I'm kind of limited on the left and right by -4 and 4. But in terms of my number types, I haven't limited things much. I've still got some larger negatives, some fractional negatives, fractional positives, larger positives, -1, 0, 1. All that stuff is still on the table at this point. So really, I'll need to take a closer look at quantity A and quantity B. So quantity A, -x, that's just my linear shape flipped vertically. And technically, I'm only looking at values between -4 and +4. But that's the basic shape of it. Now, if I go to quantity B, the opposite of the absolute value of x. So regularly, absolute value is going to be that kind of V shape. But if I have that negative sign, it's going to invert that. We're flipping it vertically. And again, we're only between -4 and +4. But you can see when I'm in quadrant 4, -x and the opposite of the absolute value of x, those are going to be equal. But things change around when I'm in quadrant 3. So I can either have these two quantities being equal or not equal, depending on what numbers I select. That means the answer has to be D. Let's do one more of these involving absolute value. Here you go. For this problem, we're not giving any upfront information, so there's nothing limiting the domain of X, right? All of these 7 areas are still on the table here. And the graph of quantity B, we've got that coefficient 2 in front of X, so it's basically taking that linear shape and just speeding it up, making it a little more aggressive. So how is quantity A going to look by comparison? So we have the absolute value of X plus the absolute value of the opposite of X. And remember, when it comes to absolute value, those two things are equivalent. No matter what X is, the absolute value of X and the absolute value of the opposite of X, it's the same number. So I can reconceptualize this as either being the absolute value of 2x or the absolute value of the opposite of 2x. Either of those, it's going to be similar to that graph of quantity B, except it cannot go negative. It must stay within quadrants 1 and 3. So kind of like what we saw in the last problem, when I have positive values of x, these two are going to be equal to one another. But when my input is negative, that's where I get some differences. So the relationship is not consistent, and the answer will be D. So earlier, when we were talking about modifiers, we saw how wrapping a cubic inside absolute values makes it look more like a parabolic even-ordered function. So now I want to ask you, how could I go the opposite direction? How would I have to modify this x squared function to get it to look more like a cubic? Anyone have any ideas? Well, it's again going to come down to absolute value. But instead of putting the entire function in absolute value symbols, what I would have to do is just put one of those x's in absolute values. So I'm breaking that square into x times x. If I put one of them in absolute values, then my parabolic shape is going to look more like a cubic shape. So on the test, if you see a single x in absolute values times a regular x in your head, recognize that's going to be a cubic shape. And that's going to allow you to tackle some problems like this with speed. Give it a shot. Chat me your answer. So when I have the absolute value of x times x, that's going to look like that cubic shape. But I also have a negative sign here. So that means things are going to get mirrored across that x-axis. And I flip the whole shape vertically. It's going to look something like this. And we want to take that shape and have it so the output is always bigger than 4. Where is that going to happen? Well, if I say that is 4, it's going to be all those points beyond, whatever that ends up being there. So it's only my large negatives that are further left than -1 on the number line. So no matter what I do, quantity A is going to be something negative. So quantity B, a positive value, will always be bigger. So B is your answer. Let me show you one more of these, and then we're going to start wrapping up. Try this one. So first thing I'm going to do here is take that upfront info where we have x over the absolute value of x is less than x. I'm going to multiply each side by the absolute value of x. So now I see I've got that x times absolute value of x. That cubic shape has to be bigger than the linear x. So graphically, something like this. So where's that red line underneath the green line? It's going to happen for my big positives, and it's going to happen with my negative fractions. So that means if I had a big positive, like the absolute value of 2, that is bigger than 1. But if I had a fractional negative, like the absolute value of negative 1/2, actually, I wrote that the wrong way. So in the original in blue, quantity A is bigger. When I've got fractional negative 1/2, that's going to make quantity B bigger. So I've got my two different relationships. We've proven the answer is D. All right, and that's how you can use function shapes to visualize the domain of X. So if you don't want to pick numbers, if you instead want to think visually, this is how you do it. So to kind of recap what we talked about, you've got your three core shapes, right? Linear, parabolic, and cubic. When you have upfront info, use that to help you visualize the domain of X. If your quantities look like that, it's less the domain of X and just like what X looks like, but still useful. And then we've got a few modifiers. We talked about how you have that negative sign. It's going to flip everything vertically over that x-axis. And if you have absolute value symbols, it's basically preventing the function from dropping below the x-axis. So that if I have the absolute value of x, normally it looks like that. If it's the absolute value, it can't go negative. So it's just going to get flipped right back up. All right, so that's going to do it for me. If you like this, you can go to this link at the bottom of your screen there. I'm also going to put it in the chat box for those of you here in the Zoom room. You can check out more free prep hours at that link there. We also open up session 1 of our 9-week course opened up free to the public. So if you want to check out what that class is like, you can check out one session for free. So I encourage you to do that. And yeah, like I said, if you want to check out more of these in the future, head to the link as well. Other than that, I'll say it was fun hanging out with y'all and talking about math today, and I wish you the best of luck with your studies. Take care.